Hello, my name is Netania Economy Hutaurok with NRP 50172510002. And now we're going to talk about the three factors that cause magma formation. So, factors number one is increase in temperature or heat driven melting. So, every rock has the minimum temperature at which partial melting begins. When rock are exposed to abnormally high heat, they begin to melt and generate magma. Now, there's a different kinds of source of excess heat, such as radioactive decay, residual primordial heat, frictional heating, and mental plumes. Temperature increase with depth at an average of 25 through 30 degrees Celsius per kilometer in the crust. In most locations, this rate is insufficient to cause melting accessible depths. But in specific tectonic setting, this gradient steepen enough to cross the solidus or the partial melting. Now for the formation locations. First is mantle plumes. Mantle plumes or hotspots is a superheated column of mantle material rises buoyantly through the mantle. As it ascends, pressure drops, decompression, and temperature remains high, triggering melting. For the example of mantle plumes or hotspots is the Hawaiian Islands. So the Hawaiian Islands sits beneath the Pacific Plate, generating basaltic magma that feeds shields volcanoes like Mauna Loa and Kilauea. Another example is Yellowstone caldera in United States of America. So Yellowstone caldera is a continental hotspot generating massive rhyolithic and basaltic eruptions. Iceland is another example of mantle plumes or hotspots. So Iceland sits atop both the mid-Atlantic ridge and a mantle plume, so making it one of the most volcanically active places on Earth. Two is continental rift, so where lithosphere stretches and thinnings, it's allowing hotter asthenosphere to rise to the surface. For example, is East African Rift System, where rifting across Kenya, Ethiopia, and Tanzania produce basaltic volcanism like Nyiragongo Oidonyo Lengai. Factor number two is decrease in pressure, or as known as decompression melting. So, rocks in the mantle are kept solid not only by temperature but by enormous confining pressure. So, at high pressure, the melting point of rock is elevated, meaning a rock that would melt at a given temperature at the surface remains solid deep in the mantle because of pressure. When pressure is rapidly reduced without a corresponding drop in temperature, the rock crosses below its solidus and begins to melt. This is called decompressing melting or adiabatic melting. And for the formation locations, first is mid-ocean ridge or divergent plate boundaries. So where the tectonic plates pull apart, creating a gap through which asthenosphere mantle wells upward, as a mantle peridotite ascends, pressures drop dramatically. This decompression melting generates basaltic magma that erupts on the ocean floor, creating a new oceanic crust. For example, is the Mid-Atlantic Ridge. separates the North and South American plates from the Eurasian African plates, produce pillow basalts continuously along its 16,000 kilometers length. Another example is East Pacific Rise, which is the fastest spreading ridge system, highly productive basaltic magma generation. And also Mid-Indian Ocean Ridge, which separates African, Antarctic, and Indo-Australian plates. 2 is Continental Rift. So, as lithosphere stretches and thins, the underlying asthenosphere rises. This pressure reduction triggers decompression, melting, even within the continental setting. For this example is Basin and Range Province, United States of America. This is an extensional tectonics causing rifting and basaltic volcanism. Another example is Graben in Europe. This is a minor rift system with associated volcanism. Also a key fact, mid-ocean ridge produce approximately 75% of all magma generated on Earth annually, making decompression, melting the dominant magma forming process globally. Factor number 3 is addition of volatiles, flux melting or lowering of melting point. Okay, so this mechanism is unique because it generates magma without adding heat or reducing pressure. Instead, the introduction of volatile compounds, primarily water or H2O, but also carbon dioxide, fluorine, and chlorine into hot mantle rock drastically lowers its melting point. So, at convergent plate boundaries, an oceanic plate is subducted beneath another plate. The descending slab carries hydrated minerals such as serpentinite, amphibole, and chloride, formed a seafloor hydrothermal alteration. Then pure water trapped in oceanic sediments and hydrous phases incorporated into the oceanic crust. As the slab descends to 100 to 150 km depth, increasing temperature and pressure cause these minerals to break down and release water into the overlying mantle wedge. This water flux lowers the solidity of the mantle, causing it to melt even at temperature lower than normal mantle melting. Now for the example of the formation locations is subduction zones or convergent plate boundaries is Pacific Ring of Fire, Cascade Range in United States of America, Andes Mountain in South America, and Japanese archipelago. Also, Indonesian arc like Indo-Australian plate subducting beneath Eurasian plate like Krakatoa, Mountain Tambora, and Mountain Merapi.